Hello everyone. In this session, let me continue the next theorem. Here I have a statement. Outer measure M star is countable subadditive, or else outer measure M star is countable subadditive, or they may ask for every set an, open set n is equal to 1 to infinity. If an is a set in a real number r, then we have to prove that M star of union n is equal to 1 to infinity, an is less than or equal to summation n is equal to 1 to infinity M star of an. Meaning is that when you are going to apply measure of union of set, union is replaced by summation, and when you are going to take measure inside. Or else one more statement I can say, if you want to take measure inside the union, I have to change union by summation sign. So that is what the property called countable subadditive. Now, before proving the statement of this theorem, let me revise the concepts that I have already done. Now, remember, as I already told you, the property of outer measure, the first property says that any open set A is subset of union n is equal to 1 to infinity collection of all open intervals in a real number R. I am repeating once again, this is from the first property of outer measure of a set. That is, any open set A is subset of union n is equal to 1 to infinity in. That is countable collection of all the open intervals in a given real number R. Now, you can also remember that I think it is seventh property of outer measure is what it is, translation invariant property. It is very important. It is asked for 4 mark in 2017. Fine. So translation invariant. If that was the case, then there will be an epsilon greater than 0 such that summation length of in is always less than measure of an open set A plus epsilon. This is already done, just I am revising this. Why? Because I am using the same concept in proving this theorem. Fine. And third property, you have to remember that when you are going to apply measure of A union B, it is always less than or equal to measure of A plus measure of B. Remember, when you are going to apply measure for A union B, it is always less than or equal to measure of A plus measure of B. You just keep all 3 points in your mind, so that I will be using these points in proving this statement. Now, coming to the proof of this statement, outer measure M star is countable subadditive. That is what we have to prove. Now, let me write proof. What is given? Given is a set n is equal to 1 to infinity is countable collection. It is understood. It is countable collection of sets. Countable collection of sets in R. Now, instead of writing all the statements, and now we have to prove M star of this countable collection, union of this countable collection is less than or equal to summation of measure of the same set. So, I have to prove equation 1. Let me take this as equation 1 to prove. I have to prove this statement. Now, suppose that if measure of a given set an is a countable collection of set. Suppose if measure of the countable collection an is equal to infinity. There will be two cases, right? Suppose if it is equal to infinity, what will be the case? So if it is equal to infinity, then there is nothing to prove. This equation 1 holds. Why? Because already this collection consists of infinite number of collection of open set. An is collection of open set which contains infinite number of open intervals or open sets. Fine. So if this measure equal to infinity, there is nothing to prove. Why? Because equation 1 holds good. It is understood. Now, suppose that if it is less than infinity, in the sense it is countable. In the sense, when it is infinite, when it is equal to infinite, then there is nothing to prove as it contains infinite number of open set. If it is less than infinity for all n, then there exists, as per the definition, then there exists a countable covering. Fine. Or else I can say union I is equal to 1 to infinity in, I. if it is less than infinity, measure of a given open set an is less than infinity, then there will be a countable covering. Union, when you are going to take union for open intervals, that will say as countable covering of all the open interval. So it is given by union I is equal to 1 to infinity in, where I is suffix. I have chosen I as a suffix. In is a collection of open intervals in a real number r. Suppose let me take this entire collection as A. I am repeating this statement once again. If measure of a open set an is less than infinity, then there exists a countable covering. Covering in the sense union of all the open sets. In is open set r, an open interval in a given real number r. So I have taken that as I. In the sense suffix I is equal to 1 to infinity. It contains infinite number of open intervals in in. Fine. So it is denoted by A. A is open cover. Is it clear? Now, remember the property just now I have told you. Translation invariant property. What it says? Summation length of in is less than m plus a plus epsilon. I am writing the same property again. I am using that property I is equal to 1 to infinity length of, since I have taken open interval as in comma I, so I am choosing the same here, is less than m star an plus epsilon usually I have. So in order to prove this statement, since epsilon is arbitrary, we can choose as our wish, or I can say as a requirement of the given theorem, I can choose this as epsilon by 2n. Fine. I am repeating once again, this is from translation invariant property. Generally what we used to write is length of in. I have written length of in comma I because I have chosen open intervals as in comma I. In is one of the sets, something like in. Instead of writing in comma I have written. Fine. So it is always less than measure of an. As per the translation invariant property, you have to get epsilon here. But requirement of this theorem, let me take epsilon by 2 power of n. Hence it is, anyhow it is arbitrary quantity. Now, let me make use of first property of outer measure of a set. What actually it says? Like an, actual property is that I have written at the beginning itself. See here, A is subset of union n is equal to 1 to infinity in. This is from the first property of outer measure of a set. Now I am using the same. An is subset of union I is equal to 1 to infinity in. Usually we used to write in, but I have considered in comma I. So that is the reason I have written like this. Now let me take union on both sides. Once again I am going to take union I is equal to 1 to infinity. An is subset of union I is equal to 1 to infinity. Since variable here is n, here also n, so I have to start with n here. Now I is, we have already taken union as per the property. So we have to take union again for n. N is equal to 1 to infinity. N is equal to I to infinity. N comma I. This is from the first property of outer measure. Again I have taken union over all n with reference to the suffix n. So n is equal to 1 to infinity I have taken on both sides. Now let me apply measure on both sides. Measure on both sides. That is I am applying m star union n is equal to 1 to infinity an. When I am going to apply measure, I have to write less than or equal to as per monotonic property. Summation, so union will become summation since I am applying measure. As per the definition, union should change to summation. You have to remember all the properties of outer measure, then only you will understand this. The minute when you apply measure, subset will become less than or equal to as per monotonic property, and union will become summation, and rest of the quantities I am writing as it is. Anyhow, since I am applying measure, I have to take length of the given interval. So let me take length. L denotes length of a given interval. Fine. Now have a look at the first statement. What I have written is somewhere here. See here. Let me take this as equation 2. See, length of n comma I is less than m star an plus epsilon by 2n. So again I have obtained the same value here. Am I correct? So extra term is summation. See here, I can directly write this as m star union n is equal to 1 to infinity, an less than or equal to as it is. Only this summation as it is I will keep, n is equal to 1 to infinity. Only this value is replacing with equation 2. From equation 2, I am writing this as m star an plus epsilon by 2 power of n. Now, what I have to prove is, look at the given statement. LHS I have already arrived. See here, m star union n is equal to 1 to infinity an. But extra term is epsilon by 2n. Anyhow, when you have only epsilon, I can neglect it since it is arbitrary. But I have epsilon by 2 power of n. Now, our aim is to change epsilon to epsilon by 2 power of n to epsilon. See here, since n is the summation value, it is ranging from 1 to infinity. I have written epsilon by 2n here. Now let me write epsilon by 2n as epsilon. Why? Because let me consider 1 by 2n. Epsilon by 2n can be written as epsilon into 1 by 2n, right? Now let me give values for n. When n is equal to 1, I'll get 1. In the sense 1 by 2. N is equal to 2, 1 by 2 square. So up to so on, it will continue. Fine. Now 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus so on you will get. Now what I do is, let me take 1 by 2 as common. Fine. Now 1 by 2 I'm going to take common. You will get 1 here. 1 plus, since 2 comes out, so 1 by 2 plus 1 by 2 square plus so on you will get. Now this is of the form 1 minus x power of minus 1. Remember the equation 1 by 1 plus x plus 1 by x square plus so on will be 1 minus x power of minus 1. So similarly I can write this as 1 by 1 minus 2 power of minus 1. Now after simplification, see here 1 by 2 as it is. 1 minus 1 by 2 is minus 1 by 2. Am I correct? 2 LCM. 2 minus 1 is 2. Right? I'm sorry. 2 minus 1 is 1. Denominator as it is, 2 power minus 1. Since I have minus 1 here, power minus 1, so I can write this in denominator. Am I correct? Or else if you are finding difficulty with this, I'll write it in one more step. See here, I'll write here 1 by 2 I keep as it is. This can be written as 1 by 1 minus 1 by 2. Am I correct? Now 1 by 2 as it is, 1, 2 minus 1 is 2 minus 1 is 1. 1 by 2 here. So when you shift, you are going to get 1 by 2 into 2. It get cancelled, so term will become 1. So I can write epsilon by 2 power of n as epsilon I can write. Why? Because 1 by 2 power of n, when you keep on giving values for n, you will get an expression of the form 1 by 2 into 1 minus 1 by 2 power of minus 1. This minus 1 I can write in the denominator. This term can be written as 1 by x form. So after simplification you will get 1. So that is the reason I can neglect 1 by 2 power of n. I can write epsilon here. So what it becomes is m star union n is equal to 1 to infinity. An is less than or equal to n is equal to 1 to infinity m star an plus epsilon. Again, if you have doubt that how I can take epsilon by 2n by epsilon, you can think like this. Epsilon by 2n I have. Fine. Now what I do is, I'll give n as 1. So epsilon common I'll take. So 1 by 2 power of n I have now. So 1 by 2 power of n, 1 by n is equal to 0, n 2. So n is equal to 1. Let me give n is equal to 0. I'm sorry, summation starting from n is equal to 1, right? So I have to give n is equal to 1. So 2 power of 1 is 2. N is equal to 2, I'll get 2 square. So this value goes on continuation. So I can write 1 by 2 common again here. So we'll get 1 plus 1 by 2 plus 1 by 2 square plus so on. Again epsilon I can keep as it is. And this 1 by 2 as it is, this can be written as 1 minus 1 by 2 power of minus 1. As for the formula, 1 plus 1 by x plus 1 by x square, so on can be written as 1 minus x power of minus 1. So that is how I have written epsilon as it is now. 1 by 2, this term can be written as 1 divided by 1 minus 2. Fine. Epsilon as it is, 1 by 2 as it is, 2 LCM I have taken. So 2 minus 1 is 1. 1 by 2 I have. In meaning is 1 divided by 1 by 2 I'll get for this term. So when you shift, you will get 2 by 1. So 2 get cancelled. I can write epsilon. So what I have proved is epsilon by 2n is epsilon. So that is why I have written this statement. Epsilon by 2n as epsilon I have written here. Clear? Now, since epsilon by 2n I have converted to epsilon as per the required procedure. So now I can neglect epsilon. So when you neglect epsilon, since epsilon is arbitrary, we can neglect here, but we cannot do the same here. Why? Because I have 2 power of n here. So after simplification of this, I have obtained epsilon by 2 power of n as epsilon. Now I can neglect this. So what I got is measure of union n is equal to 1 to infinity, an is less than or equal to n is equal to 1 to infinity m star an. Hence proved. See, this is what we have to prove is. Clear? I am revising once again. They asked us to prove outer measure M star is countable subadditive. Subadditive in the sense when you're going to apply measure for a collection of all open intervals. So, if you're going to take that measure inside, that union should changes to summation value. Fine. Now, let me choose an as countable collection of sets. Then, two cases arises. If that is not countable, in the sense that is equal to infinity. Meaning is measure of an is equal to infinity, then there is nothing to prove. Fine. Why? Because I have already have infinite number of collections here. Suppose it is less than infinity, or else we can think in another way. Suppose it is equal to infinity, we cannot prove for all the infinite values. So that should be less than infinity. Second case, if it is less than infinity, then there is a countable covering such that I have taken countable cover of all the open intervals and I have assumed that open interval as A. Now this property is from translation invariant property of outer measure. There we have epsilon, but as per the requirement of this theorem, I have chosen epsilon by 2 power of n. Now in the standard property, I used to write only in. Since I have already have suffix in, so in place of n I have written I here. Now this is from the first property of translation invariant. What I done is I have taken union over the suffix n on both sides. Fine. Now let me apply measure on both sides. So the minute when you apply measure, remember this subset will become less than or equal to and union will become summation. Fine. But here I have not changed it. Only we have to change in RHS side. So union will become summation here. Fine. So the minute when you take measure, I have to take length of the interval given. Fine. Now what I did is look at the equation 2. Length of in is already assumed that from the translation invariant property, so I have written the same here. Anyhow, I have epsilon. If I have epsilon, I can neglect. But what I have taken is epsilon by 2 power of n. So I cannot simply neglect it. What I did is I have given values for n right from n is equal to 1. Since summation value starting from 1. So after some simplification, I have obtained epsilon by 2 power of n as epsilon. So what I did is I replaced epsilon by 2 power of n with epsilon. Now epsilon is arbitrary. I can neglect this term. After neglecting, I have to write this statement as it is. This is what we have to prove. That is measure of union n is equal to 1 to infinity, an is equal to summation n is equal to 1 to infinity, measure of an. Remember, so right from here, I can directly replace wherever I have union. When you're going to take this measure inside, I can replace union with summation. This property is called as countable subadditive. This theorem is important and hence the corollary will be asked based on this theorem. Now let me look at the corollary part. So based on this theorem, we have mainly 3 corollaries. Let me prove corollary 1. An outer measure of a countable set is 0. It is important. It is asked in year 2018. Question will be like, prove that outer measure of M star is countable subadditive and hence prove an outer measure of a countable set is 0. So you have to make use of the first you have to prove this whole theorem followed by this corollary part. Now, let me prove how we are going to prove an outer measure of a countable set is 0. Now, we have to take one countable set. So, let me take that countable set as let A be any countable set. Let A be any countable set. Meaning is that it contains countable number of open sets. Fine. So, A contains a countable collection of sets. Now, right from the theorem 1 statement what it says. So if A is a countable collection of sets, we can express as union of all the collections, right? In the sense I can write this as x2 union x3 and so on. Or else I can write the same as I is equal to 1 to infinity xi I can write. Meaning is I can represent any countable set as union of all the elements, or I can say union of all the open sets which is there in the countable collection of open set A. Now what I'm going to do is let me apply measure on both sides. Measure on both sides. M star A is equal to M star union I is equal to 1 to infinity xi. What I did is just I have applied measure on both sides. Now M star of A, just now I have proved the theorem here. See here, if A is any countable collection of sets, then when you're going to apply measure, I can write that as less than or equal to n is equal to 1 to infinity. Meaning is you're going to take measure inside and you're replacing union with summation value. Now I'll apply the above theorem. By above theorem, what I can write is, I can write summation less than or equal to, equals will become less than or equal to n is equal to, I have suffix I here, so I'll use I here, but here in this case I have an, here I have, see, in place of n I have I here, so I'm using n, I is equal to 1 to infinity, summation, I'm going to take measure inside, m store of xi. I have applied measure on both sides. Now I use the above theorem. Just now I have proved the countable subadditive property I have used. So equal sign will become less than or equal to, since I am taking measure inside, so this union is become what we say summation, and measure I have taken inside. Fine. Now I think what it says, outer measure, properties of outer measure, by using the property phi. Just revise the theorem, properties of outer measure I have done. As per the property phi, what it says, measure of, outer measure of any element is equal to 0. In the sense that element should be inside the open set. So xi is equal to 0. So as per that theorem, what I can say is, as per that property, I can write measure of a is less than or equal to 0. I have replaced m of measure of xi with 0 as per property phi. So, and again, in the second property, what I have written, you just see your notes where I have written that measure of any set A is 0. This is already proved. A measure of any set A is positive. I think it is second property. I am repeating once again. As per property phi, measure of any set or any element which is inside this open set is 0 as from property phi. Again, as from properties 2, what it says, measure of any open set is positive. Positive in the sense greater than or equal to 0. Now look at the equations 1 and 2. M star of A is less than or equal to 0. M star of A is greater than or equal to 0. So clearly from 1 and 2, I can say M star of A is equal to 0. In the sense A is countable set. So I can say measure of countable set is, measure of countable set is 0. Clear? This is corollary 1. And remember, corollary 2 is there, but you don't have a proof for that. Corollary 2 says that a closed interval 0, 1 is uncountable. Uncountable in the sense the values in between 0 and 1, including 0 and 1, is uncountable. This is what corollary of the theorem. Fine. And we have corollary 3. Corollary 3, and it is important again. It is asked in the year 2018. Statement of the theorem, you have to prove theorem followed by this proof. And the corollary says that if A is measure 0 for any set A which is having measure 0, meaning is M star of A is equal to 0, then we have to prove that measure of A union B, I'm repeating once again, corollary 3 says that, hope so, corollary 1 is cleared. Fine. Now corollary 2 says that 0, 1 is uncountable. So remember the statement. Corollary 3 says that for any set A which is having measure 0, that is M star of A is equal to 0, we have to prove M star of A union B is equal to M star of B for any set B. Now let me prove. Before getting to the proof, I have told you at the beginning of this session, property of outer measure. That is M star of A union B, I can write M star of A plus M star of B. Right? So what I can write is, I'll use the same property. We know that M star of A union B is less than or equal to M star of A plus M star of B. Fine. But what is the given data is M star of A is 0. It is already given in the problem. So let me make use of that. So I can write this value will become 0. So measure of A union B is less than or equal to measure of B. But what I have to prove is equal to M star of B I have to prove. But what I have obtained is less than or equal to M star of B. Fine. Now what I can say, let me take this as equation 1. Right. Now clearly B is subset of A union B. Right? In the sense, suppose if I have set A and set B. I have obtained A union B value. B is subset of A union B, right? These properties you have to remember, but anyhow I'll give you one counter example. For each and everything I cannot give counter example. That property itself understood. So A is equal to 1, 2, 3 I have chosen. Fine. B is equal to 4, 5 I have taken. Fine. Now let me find A union B. A union B will be 1, 2, 3, 4, 5. Now you can clearly note that B is subset of A union B, right? An element 4, 5 is in A union B. See here. So B is subset of A union B. I can write B is subset of A union B. This is one of the property of set theory. Now what I am going to do is, let me apply measure on both sides. So when you do that, I'll get M store of B. Since I am applying measure here, as per monotonic property, subset will become less than or equal to A M store of, I'm applying measure, right? Measure of B is less than or equal to M store of A union B. Let me take this as equation 2. Now look at the equations 1 and 2. M store is less than or equal to M store of B. M store of B is less than or reverse of that. Equation 1, or else equation 2 I can write as M store of A union B is, I am reversing the equation, so greater than or equal to M store of B. This is something like 2 less than or equal to 1 can be written as, 2 greater than or equal to 1 can be written as 1 less than or equal to 2. Right? So in the same sense I have written this. Now look at the equations 1 and 3. Look at the equations 1 and 3. What it says, from equations 1 and 3, both are equal, right? One with less than or equal to, another with greater than or equal to. Therefore, I can write measure of A union B is equal to M store of B. Hence the proof. I am just repeating the third corollary once again. Third corollary says that we have to prove if A is any set with measure 0, meaning is M store of A is equal to 0, then I have to prove that M store of A union B is equal to M store of B. What I have done is, I have assumed the property of outer measure of a set given by M store of A union B is less than or equal to M store of A plus M store of B. Fine. From the given data, measure of A is 0. So this value will become 0, so that M store of A union B will become less than or equal to M store of B. Let me consider this as equation 1. Clearly from the properties of set, B is subset of A union B, right? I have given a counter example. I have considered two sets. So from this example, we can see clearly B is subset of A union B. That is what I have written. Now what I did is, I have taken measure on both sides. See, M star I have taken. Fine. So if that was the case, see here, I have just reversed the inequality. M star of B I have shifted to this side. So the inequality get reversed. Now look at the equations 1 and 3. One with less than or equal to, another with greater than or equal to. So from both 1 and 3, I can write M star of A union B is equal to M star of B. So a theorem followed by the corollary. This completes the theorem, and remember this theorem is very important. The theorem will be asked with corollary 1 or else corollary 3. It is important. It has been asked in 2017 and 18. Hope it is clear. The notes will be forwarded in the group. Please copy the same. See you in the next session.